Good morning, everybody. It is morning, isn't it? Time zones. So my name is Simon Sutton. I am the chairman of Study Committee D1, and so it's my pleasure to be here. It's also a little bit worrying being the first tutorial on the first day, so hopefully everything works okay. Our speaker today is Professor Uwe Schickler from the University of Graz in Austria. He'll introduce himself in a minute. And he's going to talk about technical brochure 654. Yes, got that right. On PD testing in GIS. So I won't take him into his time. I apologize for the slightly late start. Obviously, the opening session overran a little bit and coffee break was a little chaotic downstairs. But lunch is going to start a little bit later, so don't worry. You'll still get your food. And should be a great presentation. We'll have plenty of time for Q&A at the end. I guess if people have burning questions in the middle that they can interrupt you, but if not, we'll have a really good Q&A session at the end, hopefully. So, Uwe, over to you.
Yeah, thank you very much, Simon, for the kind introduction and the first explanations. So, good morning, good afternoon, good evening, wherever you're coming from and in which time zone you're still living. For me, it's, I think good morning now. Good night, yeah. Anyhow, my name is Uwe Schickler. I'm with the Graz University of Technology, and it's my pleasure to give this tutorial here in the name of Study Committee D1. As usual, we have a disclaimer for all and everything. And coming back to the first slide, the title of the tutorial is UHF, which means Ultra High Frequency Partial Discharge Detection System for GIS, Application Guide for Sensitivity Verification. And as Simon already mentioned, I will refer to the technical brochure 654 and I will try to give you all the details coming from that technical brochure. And very important, it's an application guide. So this is really a technical document where we summarized a lot of technical information. We published this in 2016. It is still valid. But at the end of the day, we did all of that for the users of GIS and to make life better, to increase reliability of GIS by the proper application of the partial discharge measurement, especially by a proper application of the UHF partial discharge detection, which can be done on site with movable, transportable partial discharge monitoring systems or within, let's say, permanent installed partial discharge monitoring system. So for the check of your GIS healthy 24/7. Disclaimer already done. So a short introduction to myself. I'm with the Institute of High Voltage Engineering and System Performance of Graz University of Technology. This is from 2014 onwards, so nearly 10 years. And in my life before, I was with one of the major Siemens high voltage switchgear factory, manufacturer of GIS, gas insulated switchgear and gas insulated transmission lines. So I was responsible for product technology, technical service, routine testing, as well as a condition monitoring on these gas insulated systems. And before that, I made my PhD in high voltage engineering in Hanover, Germany at the Schering Institute. I also have a history at CIGRE, so I'm a CIGRE member. I was thinking about since when. It must be 1998 or 1999. And I started as a young engineer, then I'm becoming a young expert. I'm still a young expert. Yeah, that's my feeling. But yeah, exactly. This was before 5 kilograms. Yeah. And you can see on the list of my CIGRE history that I already convene a few advisory groups, working groups, I received technical award from D1 and B3 in 2014 and 2022, and I'm still a member of a few SIGRA working groups which are running in the topic of partial discharge measurement and in the topic of gas insulated systems. So I think the organizers, they want to help me here on this desk, but as a professor, I'm using going up and down. So I think you can also understand me now very well, isn't it? That's great.
I think it's being recorded, Uwe, so
no, it doesn't matter. We have to talk about it later because nobody asked me for that. And after this short introduction, I think we can start now with technical content. Here on this slide, you see two brochures or two documents coming from C. the former Electra paper from 1999, which deals first time with the improvement and a kind of, let's say, standardization of the ultra-high frequency partial discharge measurement, and the 654 brochure was from the working group D125. And you can see a few nice pictures from GIS, 145 kV level up to 550 kV level. I would like to start with some basics and application of the partial discharge measurement, especially for GIS. But first, maybe I can ask you where you are coming from. Who is from utility? Hands up. Who has already seen a GIS? Who operates a GIS? Who is familiar with partial discharge measurement in general? Okay, who is knows something about the UHF, the ultra high frequency method? Okay, that's great. And who operates a full partial discharge monitoring system on his GIS? So I'm the right person here for you. That's great. So with the basics, we have to look into the electrical insulation system of GIS or GIL. In detail, we have a metal clad enclosing housing today made of aluminum gas tight. This housing is earth on earth potential. In the middle here we have the high voltage conductor with the high voltage on, and also here in this conductor the current is running. In yellow color, this is the insulating gas, which is up to now for gas insulated systems to 99.99% SF6. So for hexafluoride, nowadays we have a few prototypes already running with SF6 free gases. We call it alternative gases, based on dry air, synthetic air, or based on fluorneutrinos or fluorketones, but it's still under investigations. We have some epoxy spacers, which here puts the conductor in the center, in the middle of the gas compartment to fix it there. And what else? We have some defects. Normally, and this is really the standard solution, we have no defects in the GIS. But as you know, people are working on these modules, on the GIS manufacturing. Some trouble can occur, and sometimes we have some free particles here. There's a free particle, it's not really shown. Here's a free moving particle. And when I'm talking about particles, then I talk about metallic particles with a length of 1 millimeter, or 2 millimeters, or 3 millimeters, not meters. Very small and very lightweight, maybe some 10 milligrams. But such particles can destroy your electrical insulation system. Some particles can cause a power arc, a short circuit. So an outage, an unplanned outage of your GIS. We have the moving particle, we have particle on insulation. That means such a metallic particle from the machining of all these parts in the GIS is located on an epoxy spacer or an insulating part. We talk about protrusions. It's showing here, I think, and also here on the chamber. This is a very sharp needle-like defect with a length of 1 or 2 millimeters, which can also cause a breakdown. And we are talking about floating electrodes. That means the shielding, for example, on the conductor is not contacted well to the high voltage potential. And if this happens, there will be some firing, some partial discharges between the floating element and the high voltage conductor. And last but not least, we are talking normally about voids. It's shown here. It's a small, let's say, air-filled bubble in the epoxy spacer. And if the field strength in the bubble is high enough, we have partial discharges inside this gas cavity, this bubble, this void, which can then destroy the epoxy part. And it can end also in a disaster in the power arc of the GIS. And what we like to do with our partial discharge measurement, as well as in detail, with the ultra-high frequency partial discharge monitoring systems, we would like to avoid such pictures. All these pictures are showing some flashovers, power arcs. Here we have a flashover on the surface of an epoxy spacer. Here, shortly before repair work, the flashover in a 90-degree angle, a flashover here, a power arc, maybe some 30 kiloamps or 100 milliseconds in the compartment, and here damaged voltage transformer. When we talk about the defects, we have to think about what are the critical defects. By the way, you don't need to make pictures if you don't want, because this brochure 654 is available on eSigre for free. You can download the full brochure on the eSigre website. So in this brochure, we have this kind of this nice table here showing the type of defects, the critical defects, and the detectable lengths of these defects. And that's very important. With the partial discharge measurement, nowadays we are still limited in the detection of the critical defects to a certain amount. We will discuss this later in detail. So, when we talk about the moving particles, and these particles are really moving under AC voltage. The particle is laying down on the enclosure. When the AC voltage is high enough, these particles are lifted off and start jumping. And if you increase the voltage more and more, the particle jumps higher and higher. And if it is touching the conductor, it can initiate a flashover. So the moving particles are critical from a length of 3 to 5 millimeter, depending on the voltage level of the GIS. So that means the dimension of the electrical insulation system, the distance between conductor and the enclosure. If you think about the first generation of GIS, which started nearly early 1970s, we have big dimensions, so the particles were not so critical. But with time, we decrease the size more and more of the GIS, and particles were getting more and more dangerous, especially, let's say, in the 1990s. A lot of improvements were done during the production, quality assurance, and so on of the GIS to avoid these particles. But in general, 3 to 5 millimeter of length is critical. If we do an PD measurement according to the standard IEC 60270, such moving particles will give you an apparent charge between 2 and 10 picocoulomb. This can be easily measured in the laboratory, sometimes also on site. And here the detectable length is in the same range as the length of the critical defect. Protrusions on high voltage conductors, this means the small needle, the sharp edges on the conductor, the critical length is around 1 millimeter. Such a small defect can decrease the lightning impulse voltage withstand to 50%. This defect will give us an apparent charge of 1 to 2 picocoulomb, and the detectable length is 3 to 4 millimeters. So to make it clear, with the standard partial discharge measurement, we are not able to detect this kind of critical defect. Protrusion on enclosure, the same needle, but on the enclosure, critical length 4 to 6 millimeters, roughly 2 picocoulomb per current charge, and 10 to 15 millimeter is the detectable length. Particle on insulation, critical length 1 to 2 millimeters, about 0.5 picocoulomb. Detectable length 3 to 10 millimeters, depending on the location. If it's more close to the conductor or more close to the enclosure. But also here, it is nearly impossible to detect this defect by partial discharge measurement. And last but not least, we have the voids. 3 to 4 millimeter in diameter, 1 to 2 picocoulomb, and the detectable length and diameter is in the same range. And please remember also that for the IEC standard 62271-203, which deals with the GIS, there is a partial discharge measurement acceptance criteria defined to 5 PC during type test and routine testing according to IEC 60270. And because we are not able to detect all these critical defects, the manufacturer should work in a way that such defects are avoided. And they have to take care that all these defects are avoided by design, by manufacturing process, by quality assurance. Not only in factory, that's a routine test, also after assembly on site, where we then have to do the on-site test to ensure the diametric integrity of the GIS for the lifetime of 40, 50 years or even more. Simon already mentioned, if there are some questions in between, please raise your hand and let's discuss your question. Some basics about the PD measurement. This is the standard IEC circuit where we have the test object which is directly earthed. We have a defect here in this capacitor which represents the GIS. We have in parallel the coupling capacitor, the coupling device, the measurement instrument. I think this is part of my student exercises in the university. This is all done in the GIS factories, sometimes on site, but not applicable, let's say, for 245, for 25 kilowatts and more. And we have also to notice that this IEC 270 has some limits based on the noise level which occurs on site. In the factory, you have a Faraday cage, or you have a totally encapsulated test setup, which cancels most of the noise, and you can have a detection sensitivity of roughly 0.5 or 1 picocoulomb. This is not possible on site. There you very often have a noise level of 10, 20 picocoulomb, but very often much higher, 50 or 100 picocoulomb. You are looking so serious? Everything fine? So, and because of these drawbacks of the IEC 60270 method, in the 1980s, the UHF method was, let's say, invented. UHF means ultra high frequency, and here for GIS, UHF means the frequency range from 200 megahertz up to 2 gigahertz. Everything was done, or the first things are done at the University of Strathclyde. They developed this kind of technology. Later on, the first companies dealing with partial discharge monitoring systems based on the UHF methods were coming from Glasgow. And it's really nice to have this technique available. A few more slides are coming showing this in detail, because with this UHF method, we were able also on-site to do a very sensitive measurement, because the noise signals are very low in that frequency range. There are also other methods available for partial discharge detection. We have the acoustic method. which is also applied from time to time. We have also the optical method and the chemical method, but this is not something I would like to talk about today. By the way, two typical PD pattern. On the left-hand side, you see a diagram with the single cycle number here on that axis, the phase angle here, and the magnitude of the partial discharge in that direction. And if you look in a different way to such a diagram, we have the well-known phase resolved partial discharge chart, so the PRPD, which show us a typical pattern which is related to the phase angle. PD measurements under AC need always to do in a proper way that it is synchronized to the AC. Otherwise, we cannot have the proper pattern. For example, this is a rabbit-like pattern from a void in epoxy. Here, this is the back of the rabbit, and this is the long ear of the rabbit. This expression was introduced by some Japanese experts in the 1990s, so everybody knows that as a rabbit-like pattern. UHF PD detection more in detail. Please think about, we have a defect in a gas insulated system. Here is an example. It is shown as a protrusion on the enclosure. We increase the voltage more and more, and then we overstress the insulation strength in front of the needle, and the partial discharge will occur. These partial discharges in SF6 are very short impulses with a rise time in the range of picoseconds. And if such a partial discharge happens, some electromagnetic waves are spread out from this defect inside the tubes of the GIS or GIL. So electromagnetic waves are running through these tubes, and if we have a kind of antenna, for example in this position, and we connect an oscilloscope, we can find this signal from the PD in time domain. Please remember, the original PD pulse is within, let's say, 1 nanosecond in that example. The answer signal captured at the antenna is a ringing signal with a duration of some tenths of nanoseconds. This is based on the traveling waves inside the tubes with some reflection, some attenuation, and this signal can have a length of up to some hundreds of nanoseconds. Anyhow, we can capture the PD signal with a very simple antenna. If we have a look to the frequency domain, same example. Now we connect a spectrum analyzer here to this antenna, and this was done really in the 1990s. There was a very nice instrument, the spectrum analyzer from Hewlett-Packard, with a frequency range from 0 to 1.5 gigahertz. And all the GIS engineers at that time, they were in front of this small screen, and check out if there is PD or not. And they check it out via the frequency spectrum. And here for this example, we have a frequency spectra from 0 to 1.5 gigahertz, and we saw a lot of spectral lines in the range from, let's say, 0 to 1.2 gigahertz. And the noise level will be a straight line, maybe here in this way. Sometimes we have 1 or 2 spikes from a radar, 1.1 gigahertz, for example. But here, this broadband signal in frequency domain was generated by the partial discharge at that protrusion. So, and that's all for the basics of the ultra-high frequency PD detection. We need some instruments which can collect the signals here in time domain or in frequency domain. And as an example, I would like to show you one partial discharge monitoring system. Such systems are available on the market from different OEMs since the mid of 90s. And in general, here in blue, we have a nice GIS with one coupler set here on that position, so each phase, one coupler at that point, the other one is here. By the way, the typical distance between couplers depends on the voltage level of the GIS. And for 145 kV GIS, you have a distance of roughly, let's say, 6 to 10 meters. For 420 kV GIS, you have a distance of roughly 20 meters. For GIL, gas insulated transmission lines, which are a real perfect coaxial line, you can have a distance of some hundreds of meters. We have here in this case the connection of the couplers by shielded cables to an optical converter unit. Here the signals are digitized and changed to optical signals, and then with fiber optics we have the connection to the PDM equipment cabinet. Typical situation here, a nice cabinet with a UPS, with a computer, with a printer, and a powerful industrial type PC, which is able to store all the PD pulses 24/7 basis for some years. So we are able to measure each partial discharge for, let's say, a time of 20 or 30 years, no problem about that. And let me say with that word, nowadays these systems are also really reliable. Yeah, in the beginning it was a little bit tricky. Electronics were not so good, software was not well. Anyhow, since roughly 20 years, these systems are on a very high level, which can support the utility when looking into the details of the GIS. An example of a typical coupler, which is here in this position in the flange of the GIS, another version of such a coupler, and two typical kinds of diagrams, how to display the partial discharge activity, and the systems are nowadays also equipped with automatic PD identification. So the system itself can tell you what is a kind of defect, how critical it is, and then the system will generate an alarm, send out a warning or an alarm to the SCADA system, and show up if something is getting wrong. A few words for the basics of acoustic PD detection. Have a look on the build here on the top. We have a small discharge, maybe in the front of a protruding tip. We have some sound pressure waves caused by the partial discharge in the front of the needle. These sound pressure waves will go to the enclosure and can be detected with an acoustic sensor, similar when your doctor is checking your heartbeat. The same if a moving particle is around, the particle will jump and will hit the enclosure, and this small cling, when the particle hits the enclosure, will also cause some traveling waves in the metallic enclosure, and with the same acoustic sensor you can capture the signal. Here, one example of an acoustic PD instrument is shown. The acoustic sensor is a small, let's say, handheld sensor, which you have to held in a proper way on the enclosure. And the problem with the acoustic is that it is very time consuming because of the attenuation in the metallic flanges. You have to measure on a lot of different positions on the GIS to check for PD activity. So here for this left-hand shown example of a typical GIS, the green dots are the locations for the acoustic sensors. And if you're doing this during a high voltage test, for example, you can see the people have to go on a ladder and so on. So it's time consuming. But you have also some possibilities to show up the signature of the partial discharges also under the acoustic PD detection. You see this typical amplitude versus elevation time diagrams for a particle, and the experts can evaluate the length and the mass of the particle by such diagrams. You have some simple readings on the PD instruments which are available, which give you some information about the kind of defect. And as a summary, the acoustic PD method is very sensitive for particles. Voids cannot be detected because the attenuation of the epoxy is too high, so the sound from the partial discharge in the void will fully disappear until you can measure it with a sensor. The distance is too long for that. Testing is very time consuming. Acoustic PD instruments are available, sometimes used. Acoustic partial discharge monitoring are not in service, to the best of my knowledge. So, and after this introduction about PD measurement, we are coming to the technical brochure, or let's say to the Electra paper from 1999. Because I mentioned already, the UHF method was invented, developed in the 1980s in Strathclyde University in Glasgow. Then there was some time going around in the world. A few customers asked, utilities asked for the application of that method. The manufacturers has to follow. The third-party testing institute, they know nothing. So that was the time to decide that Siegel was set up a working group to summarize the knowledge and to prepare a nice paper. And for the first time, this was published in Electra in 1999 with the title Partial Discharge Detection System for GIS Sensitivity Verification for the UHF method and the acoustic method. And the point was that when we apply the IEC 60270 method, we have a calibrated measurement according to the standard. And the criteria, the acceptance criteria in the standards given by 5 picocoulomb can easily be read on the instrument itself. Don't forget it's in a current charge. So the acceptance criteria like 5 PC is nice to know, but this never means that 4.9 PC is good and 5.1 PC is wrong, bad, and failed. It's a current charge, and you always have for GIS to take into account the type of defect and the criticality. So at that time, anyhow, everybody was asking, I detected partial discharge. How can I compare this with the IEC 60270 method? I measure something in the UHF range. Is it 2 picocoulomb? Is it 5? Is it 10? Is it 20 picocoulomb? And this was not answered at the time in the, let's say, early 90s. And the Siegel working group, here the task force 15-73005, they worked a few years. And they are coming up with a kind of sensitivity verification. It's not calibration. They were defining a set point that in laboratory you find the level in the UHF range which is equivalent to 5 picocoulomb. That's all. But this was really one major improvement at the time, because after this publication, everything was, let's say, on the same agreed common basis. The utilities, the manufacturers, the third-party testing institutes, they have agreed on such thing. And now it was clear if we want to have a 5 PC sensitivity for PD measurement on site with the UHF method, we can do it. We have an acceptance criteria. And the sensitivity verification works in that way that we have a 2-step procedure. Step 1 needs to be done in the laboratory. Mostly this is done at the manufacturer's laboratory. And step 2, which is coming soon, has to be done on site when the GIS is fully erected. So for step 1, we want to see what is the equivalent to this 5 PC value in the UHF range. And it was very simple. We have a test arrangement which consists of the GIS test setup with a defect with 2 couplers and with a UHF measuring device. At that time, it was not defined, is it a spectrum analyzer, is it a digital instrument, or whatever. And the point is that in the first step, we have the defect here. At that time, it was always used a mobile particle, this jumping particle. We increase the voltage until the IC6270 system is showing us 5 PC from this moving particle. And then we have a reading on the UHF measuring device, magnitude. 5 PC, moving particle. We have the 5 PC on the PD instrument according IC6270. And we have the reading at the UHF device. Whatever it means. We have a reading. And now, this is also important, the next step here is to inject an artificial signal by a pulse generator, which gives us on the UHF device the same reading. If we have in both cases the same reading, we can have a look to this pulse generator, and this is the step voltage. And maybe this instrument is showing 20 volts. So then it was quite clear, sensitivity verification step 1. The result is 20 volt from the pulse generator is equivalent to 5 PC, apparent charge from IC6270. Understood? Very easy, but often this was done in the wrong way, but it's a different story. So, result. Example, a voltage step of 20 volt is equivalent to an apparent charge of 5 PC caused by a moving particle. If it is 2 volt, 5 volt, 10 volt, 20 volt, 50 volt, this depends on the design of the GIS, the size. This depends on the design of the antenna. This depends on the measurement chain, amplifier, and so on, bandwidth, and so on. So this is not a fixed value. This voltage, 20 volt, can be again 2 volt up to 50 volt, whatever, depending on the type of GIS and the kind of measuring equipment. So what we need is to have a proper document where everything is really documented. So if you nowadays specify the new GIS and you want to apply the UHF method, then your first sentence, everything needs to be documented properly. And they have to document the type of GIS, the type of antennas, the GIS arrangement, the defect, the UHF measurement device. At the end of the day, once again, you have a voltage from the pulse generator, which is equivalent to an apparent charge of 5 PC. Why 5 PC? Because it is written in the IC standard for GIS, as we said. So, first step done, document is available, everything is clear, crystal clear, then we can go on site and we can do the step 2 of these sensitivity verification. Very simple. We have the same pulse generator, we have the same antennas, we have the same type of GIS, and we have the same measuring device. What is the question now? Do we have enough sensors inside the GIS to be sure that the defect of apparent charge 5 PC can be detected by the UHF device? I told you we have, let's say, distance between couplers of roughly 20 meters as a rule of thumb for 420 kVJS. If I have only one sensor in a huge GIS 10 base, I'm not able to detect all the PDs. I have a limited view from each sensor into the GIS. So I need a certain number of sensors to really check each section of the GIS. And how can I check if I have enough sensors and that the sensors are at the correct position? This is done by the legendary step 2 of sensitivity verification. So this nice guy here, is injecting the artificial pulse, maybe this 20 volt, let's say 20 volt, inject it here, and now we have the adjacent sensor far away. We inject at the cable termination box, we measure at the bus bar, and if we can detect the injected signal, then I have the correct sensitivity between the two sensors. If this instrument is not able to detect the signal, then the distance between the sensors is too big. And we have to change the position. We have to add another sensor maybe, we have to change the position. We can also try to improve the amplification here of the measuring device. We can change the bandwidth and so on. But if we do such changes, then we have to repeat step one with the same settings which I used on site. That's important. So step two is to be done on site after the GIS is erected, shortly before the high voltage on-site test, because we want to use this system during the on-site test. Don't do first the high voltage on-site test and afterwards sensitivity verification step 2. That's the wrong sequence. The same can be done for the acoustic method. Injection here, detection there. But again, very limited application of this technology. So now we have the basics of the Electra paper from 1999. That's also free at the eSignal website. Let's talk about the technical brochure 654 from working group D125. I think we collected the knowledge, the internal experience after this 99 Electra paper. We started, I think, not exactly, maybe in the year 2011 or something like that. We finished in 2016. Here you have a look to the members of this working group. Convener, that's me. Secretary was Wojciech Otonovic. A few people which are here on the list are also sitting here in the audience. Yeah, anyhow. And this technical brochure is structured in that way that we have different chapters: introductions, fundamental UHF PD signal propagation characteristics, sensors, type of defects, step 1 and step 2, once again, but to make it more clear to everybody, to give really hard statements. The 1999 wording was a little bit weak. There was a possibility of misunderstandings, and sometimes the UHF method was not applied in the correct way. But here, really, let's say, strong definitions were taken, and that were summarized in the guidelines and recommendations chapters. And last but not least, we have the chapter with conclusion. So, and now, it's a little bit stressed by some sentences. So, as the introduction, the GIS is in operation since more than 50 years, very high reliability, but we still have some breakdowns, some power arcs, some short circuits, and the return of experience can demonstrate that at that time, most of the defects, let's say roughly 50%, are caused by defects which give us some partial discharge before. So if we are able to detect the partial discharges at an early stage, we can avoid the breakdown. And that's very important. GIS are used worldwide. This is also not new. Third bullet point, some reflections to the 1999 Hickory report, the two-step procedure, and here the last bullet point, working group D125 collects the available experience for the sensitivity verification of GIS, and the goal and the results are guidelines which help manufacturers and users in the effective application of the UHF method for PD detection on GIS. Some information about the UHF PD signal propagation. We have these electromagnetic waves which travel with the speed of light within the gas-insulated systems. Here we have information about the UHF sensors. We have some internal sensors which are already built in the factory of the design stages. For example, here this picture, and this one is showing such UHF internal sensors. But if you are lucky, your GIS is also able to be retrofitted with external sensors. Here, for example, a sensor on the inspection window, or that example, here is an external sensor on the epoxy bushing. In this working group, we discussed really heavily how to deal with the sensors and the electronics and PD instruments. Should we look for standardization of each device by itself? At the end of the study, we said, no, that's not important. We will look for the complete measurement chain. But anyhow, you can compare different sensors with each other by using some test sets and to check the sensor performance. So what is the antenna factor of your designed antenna? What is the frequency range of your antenna? And therefore, you can install such a sensor in this type of defect. Special conical tapers here are used on both sides. Signal injection on the left-hand side, on the right-hand side, you have a termination with the surge impedance, and you can measure the frequency range and the antenna factor of the UHF sensor. You can change your design, you can improve your design to make the UHF sensor better. You can use also other setups. GTEM cell can be used. You inject here a nanosecond impulse, you measure the coupler answer, and you can also improve your sensor. And another version was this conical setup for the check of the sensor performance and frequency response. Defects, we talked already about that in the introduction. There's nothing new. When we talk about the capture of the PD signals at the antenna, we have to think about some factors. And the factors are the type of defect, because the protrusion is showing a different PD pattern and a different signal answer in the UHF range compared, for example, with a moving particle. Then we need to consider the position of the defect inside the GIS. I talked about that we have maybe roughly 20 meters distance between two couplers, and if the defect is in the middle of this distance, we saw at both sensors the same magnitude. One PD signal is captured as two couplers with the same magnitude if the defect is in the middle, in between. If the sensor is very close to one defect, in other words, if the defect is very close to one sensor, we see a high magnitude on one sensor and a less signal on the other sensor, or even nothing, no signal. That is the meaning by the location of the defect within the GIS compartment. Propagation effects need to be considered. Sometimes we have a T branch in the GIS. So then the signal will already go to the left and to the right side, and this can also have an influence on the receiving signal. Characteristic of the sensors, the transfer function we already discussed, and we have to think about the data acquisition and display. Once again, charge calibration, that's not possible. Segre was showing in the electric paper a kind of sensitivity verification check, where we had these two-step procedures looking for the magnitude of an artificial pulse generator compared with the required PD detection sensitivity, in this case 5 picocoulomb. Repetition. Here a few more details about sensitivity verification. One, so really we define this kind of setup. Left-hand picture, you can see sensor C1, sensor C2 are close to each other. Yeah, some people, when they saw the 1999 paper here, they mentioned, we have to have, let's say, a compartment between these sensors. That's not necessarily true. You can have these two sensors close to each other, defect location, and here sensor C1, which is also the connection point of the pulse generator. So this kind of step one can be done on a very simple setup. Sometimes, especially for the 145 kV GIS, you can do the test also on a full day. Why not? Can be done, but this was clarified in the technical brochure. Then we have to talk about the measuring instruments, and it is possible to use narrowband systems for detection. That means in the frequency range, you make applicable only a few, let's say, limited spectral lines or a narrow band with some 100 megahertz bandwidth, or you are using a broadband system, which covers the full frequency range, let's say from 200 megahertz up to 1.5 gigahertz. But at the end of the day, this is all documented in the test report from sensitivity verification step 1. So, the artificial pulse also needed some clarification. The rise time gives an indication about the frequency which is injected into the GIS. The magnitude of the PD pulse is important, and the time between consecutive pulses. Normally this is, let's say, 1 pulse per 20 milliseconds, so a repetition rate of 100 hertz. What is written here again? The same type of pulse generator must be used for the downside test compared to step 1, very important. And now how to determine this equivalent level. So we can do this in the frequency domain. The green line is showing the frequency spectrum from a 5 dC moving particle. You can see it here from 0 to 2 gigahertz. And the blue one is the result from an artificial impulse with a magnitude of 2 volts. And do you think the blue line is covering the green line? Yes, no, maybe. So this was also, let's say, clarified in the technical brochure, how to determine the artificial pulse magnitude. And we agreed, if we are using, or if we are doing this in the frequency domain, we have to go for some statistical tools, average amplitude in the frequency spectra, measure the maximum power or the average power. And an example was given where we have these 3 criteria for the moving particle. It shows some numbers, and then we compare the 20 and 10 volt magnitude from the pulse generator. And here for this example, the output is that the 10 volt, based on these 3 criteria, is equivalent to 5 pc from a moving particle. So this is the way how to do this in the frequency domain. This is how it needs to be done in the time domain. When you have this typical PRPD from a moving particle, you see the maximum height of the PRPD chart, and that is compared with the answer here from the pulse generator. So if we have 2 volt at the pulse generator, we line up here on this scale, the magnitude of, I don't know, 10 maybe, 5 or 10, 20, 50 volts. And if you compare both signals, then you see the 20 volt is, let's say, equivalent to the 5 PC from the moving particle. So frequency domain, time domain, two different ways to determine the magnitude of the artificial pulse. And this needs to be documented with a test report of step 1, don't forget. And later on site, you have to apply the same technique as in the laboratory. If you perform this in frequency range during step 1, you have to do the same on-site in frequency domain. If you've done step 1 and documented for the time domain, you have to do step 2 on-site also in time domain. No crossover. That's not allowed. Yeah, the table showing the examples here for the moving particle. And as I mentioned before, we have to take into account the type of defect. And this was done in 2016 in the brochure for the first time. There we collected the return of experience and we saw that the protrusion is showing a different signal compared to moving particles. And if we have a test set up and we test first the moving particles, 5 PC, we went up with 10 volts. If we have a protruding tip, the needle-like defect, we end up with 2 volts. This was a major big result from that work of that working group that there's a difference. Up to that point, everything was taking, or everybody was thinking about 20 volt or 10 volt, equivalent 5P. This is the only line for criteria, the criteria to pass. But now we have to make PD measurement, we have to think about the type of defect, and then we have to look if we are passing the 5PC criteria or not. And the influence is really important. 2 volt equivalent in this example for the diffusion, 10 volt equivalent to a moving particle. And at that time we mentioned this and we gave a hint. The today running working group, and also my paper this afternoon, will make it more clear. If you want to avoid flashovers in GIS, we have to look for all kinds of defects, and we have to look for higher sensitivity. So nowadays, we are not longer talking about moving particles, because manufacturers and the people on site during assembly, they can handle these mobile particles. They do cleaning, proper design. There are some particle traps in the design of the GIS. So today, the moving particles are not longer a problem. But today, a lot of flashovers occur. Again, I have to say, during disconnector switching. And the reason for failures during disconnector switching is that at a certain point, it's a small particle which reacts to the very fast transient signal and causes a breakdown. So later on today, I will require sensitivity for an artificial, for a defect, fusion defect of 2PC. But that's a different story this afternoon. So, the second step of the signal sensitivity verification follows the first one, follows on-site after direction GIS before the high voltage test. We already have seen the general principle, and here I have one example. It's a transformer bay. Here's a transformer, the connection to the main GIS, to the bus bars, and the section is equipped with 3 sensors. One at the bus bar, one here in the section between bus bar and transformer, and the third one on the bus bar. And each manufacturer has its own rules or tools for the placement of the sensors. This is one example. If we think about this arrangement CDE, here again shown on the single line diagram, we are able really to monitor all parts of the GIS with the highest sensitivity. we came up at the technical brochure with a simplified UHF attenuation profile, which is shown here on the bottom. On the y-axis, we have the UHF signal. On the x-axis, we have the location of the different couplers, the length of the GIS. And the point is here, if we inject at center A, the signal will attenuate it and will lose magnitude versus its way inside the GIS, but at center position B, you see we are able to capture a signal. If we compare this with A and C, injection at A, we follow this UHF signal attenuation profile, so there's no signal at the coupler C. There's no need for that because we have coupler B in between, that means injection coupler B. Then we have also this attenuation in the GIS, we have a signal at sensor A and sensor C, so everything is running well. Yeah, this is an explanation for that what I've already said. The working group members discussed also another possible solution for the setup of the sensors. So let's say with a very strong interpretation of the rules, we can cover also the full GIS by the sensor B and D, because it gives us enough sensitivity. Injection at B, we have a signal at A, and here in the midpoint from D, we see at the end E, and here we have a crossover. So if we have a effect of 5 PC inside the GIS, we are able to capture it with the sensors B and D. But anyhow, from today's point of view, this is not really recommended to use such a setup for the couplers. The setup here in this way with the 5 sensors of the example is much better and more reliable. Also, the switching position of the switching devices has an impact on the UHF signal. That means on the result of sensitivity step 2. It's a very simple GIS way to busbar, circuit breaker, cable termination. You see one coupler at the busbar, one at the cable termination. And here we have the switching positions of Q1, Q2, Q0, and Q9. If we inject the signal here at the busbar, and we have the switching position open, close, 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 we end up with 100%. That's the PD instrument. If we have the switching arrangement of open, 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 we enter up with only 58%. So for the sensitivity verification step 2 on site, the working group really recommends to do this in a way with a typical switching arrangement in operation. Otherwise, you have different results here for the sensitivity verification step 2. This will conflict with the basic ideas of this technology. Similar with the frequency domain using spectrum analyzers. Coming now close to the end, only a few slides more, and then we have Q&A session. So, we end up with some statements and recommendations. Sensors, the same type of sensors must be used during step 1 and step 2 of sensitivity verification. Pulse generator, the same type of pulse generator should be used in step 1 and in step 2. Measuring equipment, same equipment during step 1 and step 2, all with a system with similar or better sensitivity. Execution, here you have the sequence how the check on site has to be done. So for each of the different GIS sections, that means the parts between two couplers, these rules have to be followed. And the first rule is to connect the pulse generator to each and every UHF PD sensor. The UHF measurement device is connected to the adjacent sensor. Then, first measurement is to check for the background noise level. Then the second measurement is done with the pulse generator switched on. and the magnitude of the measured UHF signal should be checked and documented. Also the switching position, don't forget. It should be noted that the on-site sensitivity verification can be applied during commissioning as well as during regular operation of GIS. This is for, let's say, later purpose to recheck measurements, change equipment, and so on. You can do this also on the energized GIS. That's not a problem in general, but definitely you have to do it before performing the high voltage test, because we want to use the results from the high voltage test, from the PD measurement during the high voltage test for quality assurance. And the criteria to pass the test, to pass the on-site sensitivity verification, then the artificial pulse injected and the adjacent UHF sensor should be clearly show an amplitude above the noise level. That's important. And last but not least, the technical brochure finished with this kind of tables. In total, we have, I think, 15 steps, and we describe here for the sensitivity verification everything very detailed. And if you have to do a specification for GIS, or you have to do the, let's say, monitoring of the PD measurement in laboratory and on site, then follow this list. This is a kind of checklist. One by one, tick, tick, tick. First is the aim of the sensitivity verification as summary, test setup, defect and detection sensitivity, sensor, PD measuring device. By the way, the user has to specify the required detection sensitivity. If you are following IEC rules, then you are looking for 5 PC. But then you have to say you are looking for 5 PC of a protruding tip or of a mobile particle. Make it as precise as possible in your specification. Sensors, PD measuring device, pulse generator, requirements, you can make a tick. Determination of artificial pulse magnitude. Results need to be documented, and then it's going on for step 2 on-site. Again, the aim principle, arrangement of sensors, position of switching devices, test equipment, criteria to pass the test, and result. And here the conclusion. The return of experience, and I think this is also valid today, shows that we have some defects, we have some failures and outages, and many of these defects can be detected by partial discharge in the factory during on-site testing with higher test voltages, as well as in service. And if we can detect these partial discharges, we can take some action, repair, etc., cleaning of the GIS. This will increase the reliability of GIS. The Electra report from 1999, that was the first report dealing with sensitivity verification, and from that point onwards, everybody is on the same basis. Utility, manufacturer, testing institute. The TV654 collects the available experience from the last years and described it here with this application guide, which was in 2016. And here, this is really nice. The established guidelines and recommendations will help manufacturers and users in the effective application of the UH method for detecting in GIS. And once again, TV654 is free to download. And that's it, gentlemen, ladies and gentlemen. Thank you for your attention, and I know for questions.
Yeah, so Thank you very much, Uwe, for that great overview of what's actually gone on for a long time. As you say, you're going all the way back to the 1980s and the research at Strathclyde. So the floor is open for questions.
We have a hand micro.
Somebody's running away.
And can you give your name and affiliation?
Yeah. Do we have a...
Hello, I'm Santosh Anadurai from GE. So I have a question regarding the testing at site, and how do we define the injected pulse for various types of faults? For example, how does it do we need to give a different type of pulse for each type of, for example, protrusion or particles or something like that? That's one question. And second question was, okay, sorry.
Because otherwise I will forget the first question.
Sure.
It depends. The answer is it depends. It depends on the specification which is coming from the utility. If the utility is asking for a dedicated sensitivity verification level, you can perform that on site and then it's gone. As a manufacturer, you have your responsibility. What is your responsibility of the GIS manufacturer? To survive for the first 2 years? The warranty period and then, yeah? No, from my point of view, and I'm now a third-party university guy, I can say that the GIS manufacturers, they are responsible, from my point of view, to ensure a lifetime of 50 years plus. And so the manufacturers should have an own interest in a high quality of the product, not only for the beginning, 1 to 2 years, also for the long lifetime. And that's my personal viewpoint. You have to look for highest sensitivity to detect all possible defects. And nowadays, that means you have to go for detection of protrusions. I'm pretty sure you have a different opinion. Yeah? So the end of the story is that the customer, the utility should specify what they really want to have. Then it's clear.
Just to add to a point of the 2 years warranty period, going by the bathtub model, we are not looking for a failure. We are looking for, because what we understand is this warranty period, if there is any defect, it shows up within 2 years. And as per the bathtub model, we can see that the issues could blow up within maybe first of 1 or 2 years, and it could sustain for next 40 years or 50 years, and then again ages out. So the criteria for keeping 2 years for warranty is not that it stands 2 years, but it shows up within 2 years and we can sustain. So thanks for the point again. Second point was, when it comes to an extension of a GIS, we have an old GIS and we have a new GIS, or we have some other manufacturer's GIS, and there are third-party members who are interested in installing GIS sensors in our. So how do they know and do it for us? So this is a question for you.
Simple answer, they should call me. Because if you have this topic which you mentioned, I think this is not the standard case. This is an exception for this topic, let's say. And the lucky point is if the same manufacturer is extending the old GIS, that is all in one hand. And of course, they have to follow the actual standards. But this is always a problem. If you have old equipment, maybe with some PD, and you are coming up with a new one, and the new one system is detecting PD from the old one, who is responsible for that? And let me extend your answer to question 1. Of course, also the utility is responsible for the quality of GIS. They have to do proper maintenance and so on. They should not overstress, etc. Yeah, but second question for me.
I'll give a number.
It's an interesting point, actually, the second one, because you get exactly the same questions about cable diversions and where you're splicing a new piece of cable into an old cable circuit. It's exactly the same. Any other questions? I'll come here because it's close. I'll come over there.
Thank you very much. Andreas Laubi from Orecon Engineering Consulting in Sydney. Thank you very much. Very refreshing to have a true specialist speaking in this country about that topic. It's very rare. I have two questions, short ones. The first one, the first step, you emphasized it has to be identical in the lab as on site. I understand, but when do you actually have, in terms of the arrangement, an identical situation? Yes, the bay maybe, but you also have ducting to transformers or whatever.
The equipment under step 1 should be the same, which is really then directed on site. If the manufacturer performed the test on equipment A and is delivering equipment B, then he has to repeat this first step of the sensitivity verification.
So you say equipment. I understand probably the thing is the ratio between the inner and the outer diameter, things like that. But I'm thinking about the arrangement. So length and T-junctions and so on. Does that also have to be identical?
No, for the step 1, you have a very small test time because you only want to see the magnitude of the artificial pulse. So at that step 1, we never discuss lengths or connection to cable or transformer. That's the reason why normally they use two sensors very close to each other and to forget what is coming left and right.
So at the end, that the main thing here is the impedance of the GIS.
The impedance design, which is related to the impedance, the type and size of the sensor and the equipment for measuring, which is most important because we had some instruments from the 1990s, continuous improvement. So today's equipment is not, let's say, comparable to 100% with the instruments from 1990. Yeah. So also when you change the instrument, you have to repeat the test.
Mm-hmm. Mm-hmm. Do you have another one, or?
Yeah, go quickly.
You showed one slide with the 5 sensors across, and I noticed the one between D and E. From D to E, it's attenuated much more. Is that a result of the geometry?
This is a very simplified example.
Yeah.
We came up with an ultra-high frequency attenuation profile. And it cost us hours of discussion because in truth, this is not a straight line. This is like a zigzag line, depending on the compartments in between. If you have a passive GIS module, or you have a module with a current transformer that changes, so you have this zigzag line, and this here should reflect to that. That's all.
Okay, it's a very coarse simplification.
Yes, and maybe if you want to look for a technical explanation, maybe this is a really big tube, so an increase of diameter from 500 to 1 meter 20. But you understand that, yeah? That's good.
I did the same thing 30 years ago, yes.
You did the same thing? Why didn't you remember of the work with you?
Most of them I worked with, yes.
Okay, so we will invite you for next time. Yeah?
Thank you.
You're welcome. Thank you for your questions.
Hello, Matthew Wiles from National Grid UK. I have a question along a similar vein in that we recently had a failure of some equipment which, when we'd recently connected a PD monitoring system to it and done a survey of the site, having been a relatively new build, we found no traces of PD. We then had a failure caused what we believe was by a void in an insulator, actually part of an insulated drive rod for a circuit breaker. And the theory is that the frequency emission was actually in the VHF, not UHF range. because of the positioning of the void and the type of void that it was. And therefore, the system wasn't detecting it because it was looking in UHF instead of VHF, and also because the propagation of such a lower frequency signal is different through the GIS. So I suppose my question is UHF the right band to be looking at? And is there any consideration for modifying the frequency ranges based on newer geometry GIS with more compact designs?
Yeah, thank you for your question. First, I'm correct, you are from NBC, but
National Grid.
so wonderful, because this will all not happen if not National Grid was pushing a lot the manufacturers and universities in Great Britain to deal with these UHF methods for Torness. Torness was the first GIS in Scotland where this technology was used. Yeah, so some 30 years ago. Thanks a lot for pushing so hard to get this developed. A void in an insulating rod was maybe the root cause of defect, of a threshold of power. And from, let's say, my basic understanding, a typical void should give a very broad band frequency range answer information. So the ultra high frequency method was chosen in former times based on the low number of noise signals in that frequency band. And so the UHF method has a big advantage compared with IEC 60-207. If it is better at VH, a very high frequency, which is maybe 50 to 200 kilohertz, or UHF, in that case, from my personal view, this should not give any difference. Now I would like to say for standard GIS, the UHF technology as it is, so starting at roughly 200 megahertz, that's fine and okay. Of course, maybe there are some cases where we can improve, but in that point of view, I would recommend to do a one-to-one test to check with another insulating rod in the test setup at the manufacturer site, for example, what is really the PD magnitude of that kind of defect and what is the measurement result with a proper PDM system.
We did some work with the supplier afterwards, and I don't believe they looked at what the magnitude was. They determined that the frequency was about 40 megahertz.
Okay, maybe this belongs to the test setup. We can discuss this in detail. As a general rule, I cannot say this is, let's say, a typical situation. Because if there is PD and you have a typical GIS, and a typical PD instrument, etc., then you have a more broadband signal from that, and you will not have, let's say, an overshoot resonance of 40 megahertz. So I will not accept a statement from the manufacturer.
Okay, yeah, thank you very much, Uwe, for the nice presentation. I have two questions. The first one, I would like to come back to acoustic and light detection. We have been approached by different companies that were really eager to sell us some products for light and acoustic, but our interpretation in Statnett, where I'm working to, TSO in Norway, is that if you start to have acoustic and lights, you know, it's like old car. When you have the signal for temperature of the motor, when you get the signal, it's too late. Do you have the same interpretation of acoustic and light detection? It's when you get the signal, it's too late, and consequently, it's not the best solution to do?
Also, thanks to Statnett, because Statnett was pushing a lot for the acoustics. So the first instrument was developed in Norway. And yes, I agree to you. We have the different methods for PD detection. Sometimes it will help, sometimes it can be applied if there's no UHF standards are available. What to do if you want to have, let's say, a check of your GIS. So the only chance is then, for example, to go for acoustic. And this has some advantages, moving particles, very, very sensitive. no answer, no signals for voids, etc. So, and from my experience, when I was with Siemens in former times, we had the knowledge about the acoustic PD measurement. We were trained on that, but we applied in, let's say, 1% of all cases for measurement. So it's a available technology, can be used, but with limited output. And for light, that's interesting, for optical PD measurement, we have the experience that if there is PD, which gives us some photons, some light, we can capture it with photomultipliers, for example. The technology is available, and there are 1 or 2 systems available on the market, partial discharge monitoring systems, using the light detection. But there's no light coming from voids and epoxy, if possible. And if the light emission is, let's say, covered by some epoxy parts and circuit breaker, also not so successful.
Okay, thank you. And the second question is like all the last 10 years where I did take over some new GIS equipment from the manufacturer, my interpretation or what I understood is that the manufacturer, usually they don't accept any PD. So they deliver some switchgear which is PD free. And as it was mentioned, we know that the limit is 5 picocoulombs for the site type test. No, site, I think it's 10. Never mind. Usually it's PD free. So then I was thinking either the GIS equipment is too good or the IOC is too not difficult enough. But the reality is that we don't have any PD on all the new equipment. But we as end user, we prefer to put some effort and some time on monitoring of gas than on the UHF. But nevertheless, we ask and we require to have those UHF sensors that we are using during maintenance. So each time we are commissioning a switchgear, we ask to do the UHF method at operating voltage, so then we could compare later on during the next maintenance steps, and then we could select the bay which is the most subjected to have PD, and to start to do maintenance on this one, as we know as the other one have less activity. Is that a good way to proceed?
I think first, congratulations that you have a very low, or let's say a zero failure rate with your GIS. There are some experience around from other parts of the world where are still on new equipment are some breakdowns. And maybe the manufacturers, if they are dealing with tablets, they have an eye on you, yeah? And to give you the plus or the quality, I don't know. Once again, GIS, I think it's a very reliable product. And from time to time, there is a flashover. Some are based on poor design, but with time for all manufacturers, design was improved more and more. And today, we should have a really high quality of GIS. Anyhow, people are working on that equipment. Assemble the full GIS by some smaller modules, if you think about 420 or 550 kV, for 145, 245, also some 420 kV GIS, they are delivered as a bay, which is also reduced workmanship on site, which will improve quality. So I think your way is a good way, experience is good, and if you are looking for regular PD detection, that's also a good idea. There are different opinions available in the world. Some people are buying the GIS with UHF sensors, using them for the commissioning test, and then they are out of the first beginning of the bus tube curve, and they want to apply it some 30, 40 years later. Others, like in Dubai or here in Singapore, they have partial discharge monitoring systems from day one onwards, with dedicated alarm settings. They want to know at any time everything about the dielectric integrity of the GIS. But also they will have problems because a few of the failures you cannot detect with partial discharge measurement. That's true. Welcome. Only if you have 2 questions.
Only one. I'll work on the second one while I'm asking the first one. Tim Blair from Transgrid. You mentioned in the presentation, and as is in TB654, the importance of the same test the same injection pulse generator, the same couplers, and the same or better measuring device. We have some challenges in discussing the manufacturer without using what they recommend, being able to access a measuring device of the same make and model. How can we investigate or convince or argue with the manufacturer alternative measuring devices are equivalent or better?
Very simple. You can tell them that you joined this tutorial here and carry simple to the volume and everything is clear. Yeah. No, you have to be strong. I think you're a very powerful man. You can be strong. And so, if there is some misunderstanding, or if there is some change which cannot be reflected from step 2 to step 1, no chance. A very well-known situation is that the on-site situation suddenly requires some low-pass filters to cancel out some noise signals in the higher frequency range. Maybe the radar signals, which is typically 1.1 gigahertz, or Wi-Fi signals, mobile phone signals. Suddenly it appears that in the measuring chain, there's a low-pass filter of 700 megahertz. It's a very small thing. It is erected in 2 minutes. Nobody will notice it except the commissioning engineer for the PDM and to pass the sensitivity. At the end of the day, it's wrong. Because there's a change between step 2 and step 1. If in step 1 the 700 megahertz low-pass filter was not used, then the line is broken. They have to repeat the test, or they should do it, as they have a lot of experience. They should step 1 with and without low-pass filters and so on in step 1 already. And then on site you have to see the situation, and then you have the line unbroken. Same equipment step 1, same equipment step 2. Be strong.
Any more questions? Okay, you get to ask your third one.
Sorry. I just compensate for
Is it three and 4 or just 3?
So since he asked only one question, I compensate for you. So this was regarding the, again, calibration and so on. So how do we do it for a multiple PD source? So from that, when there is, you cannot expect that there is only protrusion or there is only particle in a system. So there can be multiple source. From that, how do I do the calibration? Because when I take a calibration, my produced, for example, my test object, I take it to a lab for a calibration. That might have 2 picocoulomb or 1 picocoulomb of protrusion. And then I add 1 particle and I test it for 5 picocoulomb. So how will that correlate together? So this is what is my question. Sorry.
I think your question is a little bit difficult. First thing is, we never do a calibration. We do a sensitivity verification. Yeah? And one point was that you have 2 different defects.
Yes.
So that means the situation in service. Correct?
In service. Yes.
In service. So this is out of scope of the TV5 software. But of course, I will not say call me, you can call him. No, if you have, you have to be independent today. If you have in service more than 1 defect, then you have to sort it out, of course. And this can be done by maybe switching operation. Disconnect 1 part of the GIS and maybe by chance 1 PD defect disappears. Other point is you can try to do localization of the defect. So make time of flight measurement between these 2 couplers with the fast oscilloscope, and maybe you are getting 2 positions of the defects. And then you have to do maintenance, repair work for 1 and then the second, whatever it is.
So we did one experiment. In that, what we did was we kept the sensors since as a time of arrival answer, when we did the frequency domain analysis of the two, we saw that when the source is nearer to sensor, the frequency amplitude also is changing. So maybe that could work.
Maybe that could work, but we have to discuss this in detail. So in general, I can give you no answer for that. Sorry, yeah. Impossible.
Thank you, thank you.
But you can talk to him later. So Uwe, thank you so much. Yeah, you will. Time's up. You're over time. But we started late, and lunch is starting late, so
I traveled more than 30 hours here to Cairns, so yeah.
you get to speak this afternoon, twice. So can we thank Uwe for that great tutorial? And he will be here all week, so if there are more questions, find him and buy him a beer, and then he will talk to you. Possibly two. So thank you very much. So before people go, just in case you don't know, so the D1 session is this afternoon after lunch. We're in one of the other rooms up here, which is, let me just get it right, M10 and 11, which I think is over there somewhere. If you want to know what order the presentations are in, they're not in here, but inside the cover, there's a QR code. If you zap that, it will take you to the app. And I think the entire agenda with the timings of different presentations are in there. I've not tried it yet. That's modern technology. That's too scary for me. I like paper. So please come to the D1 session this afternoon. Uwe has 2 presentations this afternoon as well. We've also got presentations on nanomaterials, alternatives to SF6, and measurement technologies as well, and calibrations. So with that, thank you so much for coming, and hopefully see you later.